distributions. A probability distribution was when you had a set of outcomes that could happen, and then you had certain probabilities associated with those outcomes. Alex, can you close your computer for me, please? Thank you. So now we're going to go in and talk about going in and combining these data sets together, because sometimes you don't want to look at the data separately. You want to look at it all as one cohesive unit. So one thing that I'm going to point out for this particular question and questions in general, if we indicate to you that there are two independent random variables, that means they have no influence on each other, meaning the probabilities are not going to change if one occurs first and has like conditional probabilities like we've discussed before. So if you have independent random variables and you need things to happen together, that's taking the probability of A and B. And if they're independent, you can just go in and multiply the probability of A times the probability of B. And this is only true for independent events, meaning they don't have an influence on each other. Otherwise, that probability of B is going to change depending on what happened with A. So keep that in mind. For these to work, they have to work independently of each other. And I'll kind of point out in the questions, a lot of the times they just tell you it's independent events. Now, for the first question, just to kind of go over the basics of dealing with data like this, I have two random variables. I have X and I have Y, and I am going to combine them together to make random variable S. And they're telling me that the operation they want me to do is X plus Y. So I'm going to go kind of the long way first, and I'm going to go in and kind of calculate this as if it's a whole new set of data. And then we're going to talk about some rules that we can use so you don't necessarily have to go in and add these data values together every single time, because sometimes they don't even give you the data to kind of work with. So the first question says to create a probability distribution. Remember, anytime you see this, all they want you to do is make a table. So I need to make a table where I have my outcomes S and I have my probabilities of S. Now, before I kind of fill in this particular table, I have to figure out what outcomes would I get when I combine these two data sets together. So this isn't something you always have to write out. I'm just going to write it off to the side so I can kind of have some place to have it for notes. I'm going to take every single value that's in X, and I'm going to combine it with values in Y. So I have 1 for X, and I have 5 for Y. I have 1 for X, and I have 10 for Y. It's kind of like distributing, like double distributing when you're multiplying binomials. You basically want to make sure that everything gets combined together so that all combinations are represented. So like this would be 6, this would be 11, and then I would do the same thing with 2. So that would be 7, 12, and I would do the same thing with 3, 8, 13. So these are all the possible outcomes that I could get from combining these two random variables together. So I usually recommend writing them in order. Now, it's not completely necessary. You don't always have to have them in numeric order, but sometimes it's just nicer to look at, especially for those questions that they ask you when they're like, what's the probability that it's bigger than 2 or bigger than 11? Having them in order is helpful because then you don't have to pick and choose from the table. You can just look at, okay, what numbers are to the right of 11 or to the left of 11. To get the probabilities themselves. So to get the probabilities, we have to go in and take the probability of each event. Because they're independent, we can just multiply them together. So it's kind of like I'm going in and doing 0.3 times 0.4, 0.3 times 0.6, 0.2 times 0.4, 0.2 times 0.6, 0.5 times 0.4, and 0.5 times 0.6. So I'm going in and finding each of these multiplications, and I'm using those to fill in my table. So when I multiply those things together, I get 0.12, I get 0.08, I get 0.2, 0.18, 0.12, and 0.3. So I completed the probability distribution table. I have all of my outcomes listed. I have all of the probabilities associated with them listed. Now, the next part of the question wants us to go in and it wants us to find E of X, E of Y, and E of S. Now, just to kind of give you a reminder, whenever you see E of S, that just means they're looking for the expected value. And if you have the expected value, all you're looking for is the mean. So you can do this by hand. We could go in and we could multiply outcome times probability, add, outcome times probability, and add. But anytime you have questions where they go on to ask you for the standard deviation, because that's what sigma represents, anytime they go on to ask you for standard deviation, I highly suggest just going to your calculator and entering it in. So if you've forgotten those steps, I'm just going to kind of lay them out for you really quick. You're going to go to Stat. You're going to go to Edit. In L1, you're going to put your outcomes. In L2, you're going to put your probabilities. And then you're going to go to Stat, Calc, 1var Stats. This one is a little special because you have to make sure your list is L1, which is usually kind of the default on your calculators, but you need to make sure your frequency list is L2. Yes. It's math.
I'm sorry to interrupt you.
No, you're fine. She's right there.
Oh, wait.
Katie?
Yes.
This Katie? Other Katie. She's right here.
I can take her after you're done with this.
Okay. Yeah, I can send her over.
Whenever's a good time.
Okay, I will. I always forget we have two Katies. And then when I think Katie, I don't think Katie. And then when I think Katie, I don't think Katie. And then we have a Kaylin, which is also another complicating factor. Okay, so we have our calculator steps. Now, just to kind of walk you through this, I'm going to do it one time, and then the rest of the notes, I'm going to kind of just tell you what the values are. But in my calculator, I'm going to go to, and let's see if my calculator wants to cooperate today. I'm going to go to Stat, I'm going to go to Edit, and then I'm going to change my lists. L1, L2, I'm going to clear. And then I'm going to type in all of my outcomes. And then I'm going to type in all of my probabilities. They do have to match up in order, so don't mix and match for any reason. I don't imagine why you would, but it is important. So 0.18, 0.12, and 0.3. Now, if you ever find, I had a lot of people who ran into issues with getting errors from their calculator. If there is an error that they're pushing out to you when you run 1var Stats, they're going to, it's mostly because your probabilities don't add to 1 or you don't have a probability for every single outcome. So just go back to your table, double check that you typed in everything correct. I'm going to go to Stat. I'm going to go over to Calc, 1var Stats. I need to make sure my frequency list says L2, and then I hit Enter. Now, it gives you a lot of helpful information. The stuff that matters for mean and for standard deviation are the X bar, that is your average, and the sigma X, which is our standard deviation. So I got 10.2 and I got 2.6. And that is going to be exactly what I do every single time I tell you I'm putting it into my calculator, I'm running the information, because I don't want you to have to sit here and watch me type in values all day long. But this is basically the steps that we're kind of going through. So we go in, we have 10.2, and we had 2.6. And so what I'm going to do, just for the sake of notes, in case you've forgotten, this is the X bar value. This is the sigma X value from that calculator output, just as a reminder. I went ahead and I ran the X values and the Y values separately by themselves. And I got 2.2 as the mean for X and 0.87 as the standard deviation for X. and I got 8 and 2.45. So I did the same exact steps as I just did for the S table. I just did it for X only and Y only. And these are the values that came from that. Now, the reason why I kind of gave you these values is sometimes in the questions, they don't give you the tables. So yes, if they give you the tables, you can absolutely do what we just did. Combine all the values, run the data separately, get the mean, get the standard deviation, but sometimes they just give you summary statistics. If I only had the expected values and the standard deviations of Y, I could still find X plus Y. So I'm going to go in and I'm going to have 2 independent random variables. If they are dealing with, and we have 2 things, we have mean, we have standard deviation. If you're adding them together, all you have to do is take the separate expected values and you add them together. If you are subtracting them, you take the separate expected values and you subtract them. The means are what we call non-resistant. Mean is non-resistant. Basically, every single thing that you do to a set of data is going to affect the mean. If you add them together, it's going to matter. If you subtract them, it's going to matter. We're eventually going to get to transformations. If you multiply, it matters. Divide, subtract, add, whatever. The mean is going to do whatever you do to the data. So in this case, just to show you that it works, if I wanted to find E of S, not knowing what I have from the table, if I only had summary statistics, I would just be taking E of X plus E of Y. So I would take the 2.2 plus the 8, and I would get 10.2, which is exactly what I got from my running of the table where I combined all the data sets together. So mean, usually pretty easy. Most people get mean correct because it's pretty straightforward. Standard deviation is always kind of the nitpicky one. So one thing about standard deviation is it's the typical distance from the mean. So we go in, we take all those distances, and we take the square root of them. However, in order to kind of actually change the data, you must work in the variance. So what you'll see me do, sigma x is the standard deviation. I'm going to take my data and I'm going to turn it into sigma x squared, which is the variance. And hopefully that connection gets made because standard deviation is the square root. And so in order to undo a square root, we square. So whenever I go in and I actually take these values and I want to combine them together, I want to take sigma x squared and I want to add it to sigma y squared. So that is the variance value. Technically, this tiny part is the variance, but the question is asking for standard deviation. So I have to go back and I have to take the square root of everything. So this little highlighted part on the inside, this is the part that is the variance. And then to make it a square root, or to make it a standard deviation, we take the square root of both sides. Now, before your brains want to do bad math and ask, why doesn't the square root just cancel out the squareds? That cannot happen if you have addition or subtraction. So if we're adding terms together, the squareds are not going to go away. That only happens if you're multiplying terms. So don't forget to square the square root the squares. The last piece that gets to be a little bit confusing, if I take two data sets, two completely different data sets, and I combine them together, I'm always going to be increasing my variability. By adding two of my classes' grades together, I'm going to increase how different those grades are because there's more people or there's more things in the data set. So because of that, you are never decreasing standard deviation, ever, ever, ever. Even when you're subtracting values from each other, you are not decreasing your standard deviation. So whenever I go to do the subtraction, I'm going to take sigma x squared, but I'm still going to be adding it. So I'm never, ever, ever, and I'm going to make a note, never subtract for standard deviation. Even when you are subtracting data sets from each other, if you are doing standard deviation of that new combined data set, you're still going to be adding your standard deviations together. So I'm going to go in and I'm going to find the standard deviation of S, which means I'm going to take the square root of the standard deviation of x squared plus the standard deviation of y squared. The parts that I have in black are not parts that you have to have in order to get full credit. A lot of the time we generally recommend that you don't kind of write symbols and formulas out, because if you use the wrong symbol, College Board could technically penalize you for that. So we usually say just jump to the point where you're plugging in your numbers. So I had 0.87 squared plus 2.45 squared is equal to, and this comes out to be about 2.59988. But if I kind of round that to one decimal place, like I have in my original calculation, it's going to be 2.6, which matches what we get from the data set of combined values. Now, you guys know I don't spend a ton of time on formulas because for the most part, I tell you it's on the formula chart. Don't worry about it. You're not going to have to know it. It'll be there. For combining random variables, it is the one instance where the formulas are not on the formula chart. So you have to actually memorize these. Now, a lot of it becomes intuitive, but I know I have my people who will do better by just being told you need to memorize these. You got to know these. They are not on your test. They are not on the AP exam. You have to know the basic properties of combining random variables together. Really, the means I wouldn't worry about too much. You do what they tell you to do. It's the standard deviation ones that you have to make sure you know how to work with. So let's go in and let's talk about going and doing transformations. So linear transformations basically mean we're going in and we are adding, subtracting, multiplying, dividing, whatever. A lot of the time you could have something where you are going to add or subtract, and then you're going to multiply, but you're changing your variable, your random variable, in some way, shape, or form. So I have the head folks at Google decided to try a random salary assignment, and they said that they are going to have the following probability distribution where X represents the salary. So in this case, they're telling me what my random variable is. Now, in order to calculate the expected salary for a Google employee, what is the standard deviation? This is me. I would go straight to my calculator. I would do 1 var stats. So that would mean putting X in L1, P of X in L2, and these are the exact same steps I did before, but just to save time, when I did that, I got mu of X is 64,000. Anytime you're reporting a mean or a standard deviation, you do need to have units. So since this is money, I'm going to make it a $sign. And then for my standard deviation, I have 9,165.15. And usually outside of calculating probabilities, rounding to 2 decimal places is completely fine. I'm doing 2 especially because it's money, and anytime you see money, it's usually 2 cents rounded. So I have 9,165.15. Again, these 2 numbers came directly from my calculator. I plugged in my values. I ran L1, I ran L2 on 1 var stats, and this is what I got. Now, Google then goes on and they decide they're going to give everyone a $500 bonus. Everyone's going to increase by $500. Create a new probability distribution and find the expected value in standard deviation. So I'm going to go ahead and call this B. So for B, I'm taking all of the outcomes in X and I'm going to add $500 to every single outcome. So all of the values are increasing by the same amount. So when I go to write out my probability distribution table, B, probability of B, every single amount that I have is just increasing by $500. Now, the question itself doesn't say that the probabilities are changing. They don't say anything about those values being different. So I'm going to keep the probabilities the same. So 0.2, 0.3, 0.4, and 0.1. And so now that I have my probability distribution, I go in again and I run the mean and I run the standard deviation. And that's going to be using now my outcomes as 50,500, 60,500, and so on. But the probabilities will not change. So all I did to get this next set of data is I just changed my outcomes in L1 and I got a mean of 64,500. And I got a standard deviation. Oop, it's not B. I mean, it's not X, it's B. We'll be precise. Erase. Mu of B, sigma B. I got a standard deviation of $9,165.15. So a couple of things to notice here. The mean increased, and hopefully that whole connection of the mean being non-resistant is kind of making sense. So the mean increased by $500, which kind of lines up with the fact that all of the data points increased by $500. And in the standard deviation did not change. So a little talk about that. Whenever I increase all my values by the same amount, standard deviation only represents the distance to the mean. So if everything is increasing by the same amount, those distances have not changed. Yes, they're in a different place, but they're all still the same distance apart. So standard deviation isn't going to be affected by adding or subtracting a constant. So let's kind of look at what multiplying does. So they say, or dividing, they say Google now decides, okay, we're going to pay cash at the end of the year and we're going to pay $100 bills. So everyone's getting their salary at the end of the year in $100 bills. And they say to let X, but since we've already used X, I'm going to just change this to Y. Let Y be the number of $100 bills they will give out. So Y is going to be, and they're saying to use the bonus distribution. So I'm going to take that bonus value and I'm going to divide it by 100. So that's going to tell me how many $100 bills everyone should get. So Y, probability of Y, that's 505, 605, 705, 805. And again, they have not said anything about these probabilities changing. So I'm going to keep this as 0.2, 0.3, 0.4, and 0.1. Run the same thing, take my data, change L1, one var stats, and that tells me that the mu of X is now going to be 645 bills because they're getting $100 bills. And again, you want to make sure you have units. The standard deviation, it's not X. I'm just so used to writing X. Y. The standard deviation is 91.65 bills. So hopefully what you noticed for this particular operation is from part B, where I had 64,500, 9,165. I went in and the operation I did, the division by 100, it affected both. So both mean and standard deviation were divided by 100. And so again, the mean is going to do whatever you want. If you're dividing, multiplying, adding, subtracting, it's going to change everything. But for standard deviation, the only thing that is ever going to affect standard deviation is dividing or multiplying. So if you're only adding a constant to something, your standard deviation does not change at all because you're adding the same value. So to kind of formalize that in some equations, if I am applying transformations to the mean, every single thing that you do is going to affect the mean. So addition, subtraction, multiplication, division all apply. For standard deviation, the only thing that's going to affect standard deviation is you're going to take whatever that scalar is, and it doesn't matter if it's positive or negative because standard deviations have to be positive because of the nature of taking a square root of something. So take the absolute value of it, make sure that this is a positive scalar, whatever it may be. And you're going to just use that to change the standard deviation. So I just kept it as b because b could be a fraction, which is division, and this is going to be multiplying and dividing only. Now, you will have questions where they're going to ask you, what is the new standard deviation? And they're going to give you different operations. It just depends on if you're finding the mean, do everything. But if you're finding standard deviation, only do multiplication and division. Now, this is another one where I don't spend a ton of time on formulas, but these are ones that are not on the formula chart. So you have to make sure you know these for your test, for the AP exam and for your test. Memorize them. Again, I wouldn't worry too much about means. Standard deviation is the one that most people get wrong. Okay, let's run through 2 examples and see how they could actually ask these questions. So we have an upcoming concert. They're purchasing tickets for children and adults. They're letting C be the number of child tickets purchased by a single customer. So remember, random variables have to represent a numerical outcome. So I can either buy 0 tickets for children or I can buy 3 tickets for children, up to 3. The probability distribution of the number of child tickets purchased is given in the table below. Compute the mean and standard deviation of C. So again, I would go straight to 1var stats. I would put this as L1, I would put this as L2, and just for the sake of time, mu of C ends up being 1 child ticket. Oops, ticket. Bless you. And standard deviation of C ends up being 1 child ticket. Which makes sense. I had a lot of people who were confused as to like, why is it 1 and things like that. But think about our outcomes. It's between 0 and 3. I can't have a standard deviation of like 15. I can't have negative 15 tickets in this case. So 1 makes the most sense. Now, just as a little tidbit, if I only had to find mean, so say for instance, the question did not ask me about standard deviation, I don't always immediately jump to the calculator because you can also find mean by just going in and taking the outcomes times the probabilities and getting your expected value that way. And sometimes that goes a little bit faster than plugging in your data into L1 and L2, running your calculator, getting the value. And a lot of people can just plug this into the main menu and get their answer. Now, if they ask me for standard deviation, I'm never willingly doing standard deviation by hand. So I would go to the calculator in that instance. And if you're going anyway, you might as well just get the mean while you're there. But if it's just a mean question only, I may just take the approach of doing the multiplying and getting it that way. Okay, now suppose the mean and the standard deviation for number of adult tickets purchased by a single customer are 2 and 1.2 respectively. So mu of A is 2, standard deviation of A is 1.2. And what you'll find, because I'm going to kind of explain it as I get to these, if I'm reading a question and they're giving me information, I usually rewrite it myself to kind of organize it outside of all of the words that College Board likes to include. So I can look at this and know what the mean and standard deviation is without having to reread the entire question. Assume the numbers of child tickets and adult tickets are independent, random variables. Compute the mean and standard deviation of the total number of adult and child tickets. Let's just do total number. purchased by a single customer. So I'm going to define this as T, just for total. I'm going to take adult plus child. And usually what you'll want to do is define how you are combining these random variables. So when I go in to find the mean of T, I can go in and take, and again, you don't have to write this, the mean of A plus the mean of C. And so I'm taking 1 or 2. 2 plus 1 is 3 tickets. And this is a question where you didn't have the option to combine the data sets together because we don't have data for adults. We only have data for children and then the average and standard deviation for adults. And then for the standard deviation, now the big thing that I saw a lot of people struggling with on the math lab was knowing when are we doing transformations, when are we doing combining random variables, because those are two different rules. You have to remember that if you see two letters, even if they're the same letter twice, if you see two letters together, that is combining random variables. So I have an A, I have a C, so that means I need to go in and work in variance. So that's those standard deviations squared, and then I need to come in and take the square root at the end because A and C are two separate random variables. And so that's going to give me the square root of, in this case, it's 1.2 squared plus 1 squared, which ends up being, what did I get? 1.56 tickets. So standard deviation and mean, just from using our rules. Now, then they go on to say, suppose each child ticket costs $15 and each adult ticket costs $25. So they're introducing a new element where we have the cost of each ticket and they want us to compute the mean and the standard deviation. So I'm going to call this, compute the mean, the total amount spent. Spent, we'll do S. So I'm going to take the adult tickets and multiply them by 25. I'm going to take the child tickets and multiply them by 15. And then I'm going to find the mean and the standard deviation of this transformed equation. So for the mean of S, and if you ever see things where it's an E, don't forget that that means the exact same thing. I could also be saying E of S, and I'm doing the exact same thing. I'm going to take, in the case of mean, you do everything that you see. I'm going to take 25 times the mu of A plus 15 times the mu of C. Again, the stuff in black, you don't necessarily have to write. It's just for the sake of us having notes later. I'm going to do 25 times 2 plus 15 times 1. And that's going to give us a amount of $65. Now for standard deviation, I'm still dealing with random variables being combined, but I'm also doing a transformation. So when I go in to do the standard deviation of S, I have to remember, and this isn't something we necessarily formalize as a formula that you need to memorize, but I'm going to kind of write it out. I'm going to take that 25 times the mu of A first, and then I'm going to square it. So the squared has to also apply to the scalar that you're using. So this is one way you can think of it where they're both in parentheses, they're both getting squared. A lot of people also prefer to see it as I'm taking 25 and I'm squaring it, or 15, wrong number. 15, and I'm squaring it, and I'm taking mu of C, or not mu, sigma. Symbols. Sigma, mu, sigma C squared. It doesn't matter which way you think of it. The only thing that is important is that you know that that scalar is also getting squared. In the cases of these being multiple choice questions, they will sometimes have the answer choice where people forget to square the scalar as one of the answer choices. So they get really tricky on these when they pop up on the AP exam. So I'm going to go in and I'm going to fill in the actual values that I have. So square root of 25 times my standard deviation for adults was 1.2 squared. Personally, I like the parentheses, so that's what I usually use. 15 times 1 squared. And when I plug all of this in, I get about $33.54. So again, anytime you see two letters, even if they are the same letter twice, because sometimes you'll see things like x plus x plus x, that is still combining random variables. So that still is going to take the rules that we did on the first page. So even if it's the same thing again and again and again, it's still taking two random variables that are independent and putting them together. So if you're doing standard deviation, you have to use the square root variance formula. So keep that in mind. Okay, last one. Last one was actually a AP FRQ. I like to include it because when you read through it, it seems like, what the heck are they even asking me? But again, when I see these College Board questions, I try to pull out the information. I try to make it so that it's digestible and it's not completely overwhelming with what they're telling me, because they're going to be very, very descriptive. We're going to talk eggs and they're going to be like, there is a carton. The eggs go in the carton. The carton weighs something, like all of these things. So it's very descriptive, but I don't need all that information to overwhelm me when I'm trying to answer an FRQ. So in this case, they say each full carton of eggs consists of one randomly selected empty cardboard container and 12 randomly selected eggs. So that seems important. So I'm going to go in, I'm going to say a full carton is equal to an empty container plus 12 eggs. Makes sense. The weights of such full cartons are approximately normal, with a mean of 840 and a standard deviation of 7.9. So I'm going to kind of pull that information out. Mean of 840, standard deviation of 7.9. Again, just so I don't have to read through the question 2 or 3 times to get what I need. The weights of the empty cardboard containers have a mean of 20 and a standard deviation of 1.7. It is reasonable to assume independence, which is important, between the weights of the empty cardboard container and the weights of the eggs. It is also reasonable to assume independence among the weights of the 12 eggs that are randomly selected for a full carton. Now, really, with what I wrote down separate from the entire paragraph, I don't really need anything else from the question, from the first paragraphs. I just kind of jumped to, what are they actually going to want me to do? So they're saying, let X be the weight of a single randomly selected egg. So I'm trying to figure out, what do these eggs weigh? So I'm trying to find the mean and eventually the standard deviation. So a couple of ways you can approach this. For the mean, this year that they did it, I need to go pull the grading rubric on it. Most people got the mean right, because they're like, okay, I'm trying to solve for eggs. I'm going to go in and I'm doing the mean first. I'm going to take the full carton, which is 840. I'm going to take the empty container, which is 20. And I know that there are 12 eggs, so 12 mu x. And they solved for mu of x, which is right, which is correct, which is what you should be doing. So I'm going to go in, I'm going to subtract 20, 820 equals to 12 mu of x, divide by 12, divide by 12. And then after we do 820 divided by 12, that tells me 68.33 grams is the average weight of each egg. So a lot of people this year got the mean part correct, because they're like, okay, we got eggs. That's great. Solve for X. where a lot of people went wrong was on the standard deviation part. So a lot of people kind of did the same setup for standard deviation. They plugged in 7.9, they plugged in 1.7, and they tried to solve for sigma x exactly as it is, as if they were linear transformations. However, the issue that arises is they told us in the question that all of these eggs are independent. So what's really happening in this problem is we're taking that full carton, we're making it an empty carton, but whenever I go in to say 12 eggs, I'm actually doing like, and I'm going to use X because that's what they used, X1 plus X2 plus X3 plus blah, 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 all the way to X12. So yes, you can write it as 12 times that because there's 12 of them and they're being added. However, you also have to remember that each of these eggs are their own independent random variable. So in order to calculate standard deviation, we have to go in and we have to use that rule where if I'm going to be combining things together, I need to be working in variance. So I need to not only square all of my standard deviations, but I eventually need to go on and I need to take the square root at the very end and solve it that way. So the approach initially is roughly the same. I'm going to go in, I'm going to set the standard deviation for the full carton equal to, but instead of keeping it as just 1.7 squared, standard deviation is the square root of all of those values squared. So I'm going to have 1.7 squared, and then it's going to be technically, though we're not going to write it like this the entire time, it's going to be taking the weight of each egg all the way up until x2 or x12 squared. Make that look a little better. Now, what some other common mistakes became? Yes, you can also write this as 7.9 equals the square root. I'm going to simplify this 1.7 squared just to make life easier. 2.89. You can think of this as 12 times sigma x squared. Now, a lot of people did get to the point where they knew they were doing square roots, but they also tried to square the 12 as a scalar. The 12 is not necessarily a scalar. It's just saying we have these terms 12 times. I'm not increasing the values by 12. I have 12 of them. So that's kind of where people got confused. And at this point, it's solving for a random variable. So I would go in, I would square both sides, square, square. 7.9 squared is 62.41. 2.89 plus 12 sigma x squared. And then I would subtract 2.89, subtract 2.89, 59.52, 12 sigma x squared. And then we're going in and we are dividing by 12, 59.52 divided by 12. 4.96 equals sigma x squared. Now, if this question only wanted the variance, this would be the stopping point because I have sigma x squared. This is my variance value. But they wanted us to go in and find standard deviation. So I have to come in and take the square root of both sides to take it all the way to standard deviation. So 2.23 grams is equal to sigma x. So again, a common mistake for these types of questions is people don't remember that they are taking two variables and combining them together. If you see two letters, if there are two things, you have to make sure that you're going in, converting it to a variance, and then finding the standard deviation. You guys will have a math lab where they will